Good day, grade 12 learners. Welcome to today's physical science lesson. My name is Mashidu Mambur. This lesson is brought to you by the Gauteng Department of Education in collaboration with Saibono Discovery Center. Thank you and welcome to this lesson. Today we'll be focusing on electrodynamics. So that is our topic for the day, hoping that you will be able to get the marks that this topic brings for us. Is part of paper 1 as indicated in this slide. To say paper 1 is part of the electricity and magnetism, which have 55 marks. So it's a lot of marks there. If we check this term, we are focusing mostly on topics that have to do with the electron. If we check, you have done electricity, which had the electron, the charges that are flowing. You were calculating current, which is the rate of flow of charges. So you are now today will be doing electrodynamics, as well would be having charges that are flowing from positive to negative as we move. We'll see as we move. So it's still part of this electricity and magnetism. And then we are saying that paper 1 is still 150 marks. You still be writing it for 3 hours, 180 minutes. Now, paper 1, the structure. We always remind you to know that multiple choice questions are important. You have 20 marks that is allocated to multiple choice questions, and you have structured questions with 130 marks. The total of paper 1 is still 150, as indicated is 3 hours. If you can check, if you take 3 hours, which is 180 minutes, you divide by 150 marks, you will see that for each mark, you are allocated about 1.2 minutes. So if you want to time yourself, have that in mind. To say for every 1 mark that you have to get, you have about a minute to do that. If you have 2, like in multiple choice questions, you have 2 marks for each, meaning that for each question you will spend about 2.4 minutes. You can just allocate at least 2 minutes for each multiple choice questions, which means for that 20 marks, you will just multiply by that 1,2, then it will give you the time that you will spend on that particular question. Now, our topic, which is electrodynamics, I felt it important that we start with this diagram to indicate or highlight what are we supposed to do in terms of this topic. You have done electrodynamics in grade 11. I hope you still remember what you have done. So the aim of this lesson, we will start and remind you a little bit of what you have done. You remember you've done Faraday's law as well in grade 11. So we'll focus on those as well to remind you where we're coming from, because we're taking you from the known to unknown. So we're bringing new information, but we are first starting with the information that you already know. So I will take some of the questions that you have done in grade 11 that are applicable in grade 12, because we are not starting the foundation. The house was built in grade 11. We just continue to build the same house of electrodynamics. Now we are saying our focus will be on generators and motors. See, this topic is about generators and motors. So you know the generator, the normal generator that you are using at home. You know the motor that you are using on your different equipments that have some rotation, like your fans and all that have a motor in them. So we'll be looking at those, the motors and the generators. And we're saying these generators, they are either direct current generators or alternating current generators. So we'll be looking at generators that are producing producing direct current or alternating current. And you know that as for motors, they use electricity. So we have motors that are referred to as direct current and motors that are referred to as alternating current. So you have to always remember that between our generators and motors, I think you are understanding me now. I'm saying generators, as the name say, generate. They produce electricity, while motors, they use electricity. You can look at your utensils that you use at home, that you plug on your wall there, and you are able to get your mechanical energy. So when you will see, when we are defining a generator, we're going to define the generator to say a generator converts. So we're looking at the energy conversion to say from which energy to which energy. So with the generator, we start with mechanical energy. Mechanical energy, we convert it to electrical energy. So you don't have to forget that generators, they are generating electricity. Hence, we're saying we're going to take mechanical energy, we convert it to electrical energy. And when it comes to motors, the motor itself we're going to start with electricity. We're using the electricity now. We're saying we're going to convert electrical energy to mechanical energy. So you can see how you will define your generator. You will say it converts mechanical energy to electrical energy, while your motor converts electrical energy to mechanical energy. And I've already indicated that for both generator and motors, we have DC and AC. And one thing that you must know is that how will I know that this is a direct current generator? And how will I know this is a direct current motor? We'll be focusing on that to say, how will you identify? Remember, a generator, it must be able to have something that an output, which is electricity that is being produced. But for a motor, there must be input, which means we must have a source, we must have a cell, a battery that is supplying now the motor with electricity. So you got to see that whether is we have output. When we have output, we're going to be talking about generators. When we have input of direct current, we will be talking about a motor in that fashion. So we're going to differentiate those. I hope this will help you to see the difference. The other thing that we're going to focus on, we're going to look at the principles that these motors and generators use. You will see that the generators, they use electromagnetic induction, and the motor, they use what we refer to as motor effect. So we'll be looking at those principles. The other thing we'll be looking at the components. As I indicated that we have a DC and AC. So we're going to say, how will I know that this is a DC motor or generator? Then we're going to look at the components that will help us to identify the difference between an AC and a DC. And the other thing, we're going to look at the functions of these components. What is the function of these components? How do they work? So we'll focus on that. The next thing that we'll focus on is what we refer to as RMS potential difference, or root mean square value potential difference, or root mean square value current. So we'll be looking at them is the RMS potential difference and RMS current. We'll be looking at that. And if you look at previous papers, you will have seen that most papers now you are asked to define what is RMS potential difference, what is RMS current. So we'll be looking at that to say, how do you define this RMS potential difference and RMS current? I will by all means try and show you how to simplify and to remember the definition so that you are able to define them and see the difference between the two. The next thing, we'll be using equations to solve problems. So we'll be doing problem solving, where we'll do the normal, where you will read. After reading, you will be able to go collect data and be able to identify the formula, substitute, you write the answer with the correct SI unit. So we're going to do that. Lastly, we're going to look at the graphs to say there are graphs. There is graph of AC and graphs of DC. You will see the difference there between the graph of DC, which you will see that it periodically does not change direction. So it's in the same direction. Whereas for the AC, you will see that it alternates the direction between the positive and the negative. So this will be the graph of potential difference, which is measured in voltage versus time in seconds. So we are saying the graph of alternating current will look like that, one full cycle. The graph of direct current will look like that, one full second. We'll still be having potential difference and time here in your x-axis. So you're able to know the difference between those two graphs. To see, when I see this graph, I will know this is the graph of direct current. This is the graph of alternating current. So with all, when you look at this page, you are able already to have a picture of the things that we're going to focus on. So this will be the focus of our lesson. And if you are able to remember everything that is on this slide, it means you are ready for your exams. And we're hoping we'll be able to help you and make sure that come exam time, you are able to enjoy the topic. Now, as I indicated, that we are going to start with prior knowledge to say you are not empty, you have done grade 11. What is that you have done in grade 11 before you arrive in grade 12? You will have seen questions like this one. If you look here, they're saying, in which one of the sketches below is the induced polarity of the coil correctly indicated? So we're checking here whether you still remember what happens. You will see we're having a magnet that is being pushed into the coil. So we're having the coil, all this diagram, that is your coil, that is your coil, that is your coil. All those are your coils. Now we're bringing the magnet, but the most important thing, remember the magnet has both the North Pole and the South Pole. And this is just the normal magnet that you know. It has the North Pole and the South Pole. So what happens when you take the magnet and push it into the coil? That is this question is all about. According to this, it's saying when you bring the North Pole inside the coil will induce North Pole. So the coil becomes North Pole, which means now it will repel. It will like to repel to say, no, where are you going? You North Pole, don't come in. Hence, it becomes North Pole. Remember, this movement of the magnet, the movement between the magnet and the coil, that is what is going to change magnetic flux. So it's very much important that you understand. So if we look at option number B there, they are saying when the magnet is pushed inside the North Pole, the coil will become South Pole. That is incorrect. Remember, the correct is that when the North Pole approaches the coil must induce the North Pole so that it can repel. It can repel that magnet. So this option will be wrong. Now, when you look at option number C, they are saying when you pull the magnet out of the coil, it's going away. You know that this is the South Pole here. If this is the North Pole, this is the South Pole. Now, when you are moving the South Pole here, then what must the magnet do, the coil do? The coil must become the North Pole so that it can attract the magnet not to go away. So that's how magnetic flux changes. It changes like that. We're saying when the South Pole moves away, the coil will become North Pole so that it can attract it back. So that's what it will do. But if you look at options, then that makes option C wrong because it's saying it is the South Pole. When you are moving the North Pole away, according to this diagram, it's saying when the North Pole is moving away, the coil will become North Pole. No, it must be South Pole so that it can attract it. So when something is coming towards, or when a magnet is coming towards the coil becomes North and repel. If North is coming towards, the coil will become North so that it can repel. And then we'll have a change in magnetic flux there. But now all these options, B, C, D, they are wrong. The only option that gives us the correct answer is option number A, because it's showing that when the magnet approaches the coil will become the North Pole so that it can repel. So you got to choose option number A there as your correct answer. I hope you got that. This is how the change in the magnetic field flux is happening. Now, when we move to the next question, which is question number 2 there, it says a circular coil is placed inside a magnetic field. Is inside a magnetic field and rotated clockwise to induce an EMF. Which one of the following changes will increase the induced EMF? So remember, they are saying to increase the induced EMF, we must rotate the coil slower. That will be wrong. Remember, to increase the magnetic flux, the change in magnetic flux, we must be able to rotate it much faster. So slower is wrong. It cannot increase the induced EMF. But what we are learning here is that we have to rotate the coil much faster in order to increase the induced EMF. Now, number B is saying decreasing the number of turns or windings on the coil. As well, this will be wrong because it's saying decreasing the number of turns. We must increase the number of turns in order to increase the induced EMF. And if you look at number C, say increasing the speed of rotation, that will be correct. If you increase the speed of rotation, you'll increase the induced current, EMF. So what am I saying? We're saying these are the factors that will affect the induced EMF. If you want to increase the induced EMF, we're saying you must the coil must be rotated much faster. We're saying there must be increasing number of turns and there must be increasing speed of rotation of the coil. So those are the 3 factors that will increase the amount of induced EMF. So my correct answer there will be number C. Hoping that you have done this in grade 11. Even if you haven't done, we're teaching you now, you are able to remember and know that when we want to increase induced EMF, those are the three things that will increase. The rotation of the coil will be much faster. You will increase the number of windings or turns. You will increase the speed of rotation of the coil. Now let's look at number 3. It's saying the north pole of a bar magnet is pushed into a solenoid. So we're still talking about the same concept, that when the north pole is pushed, remember where X is, you know that the magnet now will become the north pole. Remember we said when the north pole approaches, the magnet will become north pole so that it can repel. So it's able to become the north there. But the question now is about the current that is flowing there, to say in which direction will the induced current flow. Right, only from A to B or from B to A. So you got to know that if the inducing action is from A to B, is moving there to the right, you must know that the inducing action in relation to Lenz's law will oppose that motion, which will be B to A. So it will be induced in the opposite direction of the where that magnet is going, which is now from B to A. I hope you got that. The last assessment that you have done some calculations in your grade 11 where you were doing calculations. You said a circular coil. You can see we have a coil there that is circular of radius 3 centimeters. It's important to know the conventions of centimeters, millimeters, and all kilometers and all that, so that you are able to convert them to meters when you do your calculations, where it contains 150 loops and a resistance of 10 ohms. Hence, we are saying a physical science learner must have a highlighter when they are writing the exams, because we want you to highlight those values that is given information. And we are saying it is positioned perpendicular to a magnetic field of strength. So we have magnetic field strength of 3,8 T. 3,8 T. Magnetic field strength is this one that is given by B. The coil is pulled from the field in 0,2 seconds. So you are given time, you are given magnetic field strength of 3,8 Tesla, you are given the resistance of 20 ohms, you are given 150 loops, you are given the radius of 3 centimeters. And there are 3 questions that we are expected to calculate there. We have to calculate the change in magnetic flux in the coil, the induced EMF in the coil, and the induced current. So the 3 things that we're calculating is the change in magnetic flux. Don't forget, change is always final minus initial. So when you're calculating change, don't forget it's always final. What do you have finally? What did you have initially? So change all the time is final minus initial. So you got to know the magnetic flux that we have final and the magnetic flux that we had initially. And then the induced EMF in the coil, remember, in accordance to Faraday's law, that says the rate of change in magnetic flux is that is your induced EMF is equal to the rate of change in magnetic flux. So you got to remember that, and it will help you as you answer that questions. And with no wasting of time, you can see when you calculate the change in magnetic flux, you will first do the data collection, where you wrote your magnetic field strength of 3,8 Teslas. You had a resistance of 10 ohms. You have area. Remember, A stands for area, and our area is pi r squared. Then you are able to calculate your area, and then you are able to look at the number of loops there, which was 150. And then we have our time that was taken was 0,2 seconds. And then if you look at your formula for magnetic flux, is that B times A, which is magnetic field strength times area, and then our magnetic field strength was 3,8. As you calculate, we will advise you not to include the SI units. Just write 3,8 times 0,03. You can see the 0,03, the 3 centimeters, you have to convert it first to meters. Hence, we got 0,03. You multiply that, you get 0,011 Webers, and then you are able now to calculate the change. The change is final minus initial. Remember, it was moving out. You didn't have any change in magnetic flux finally, but initially it was 0.11. And if you are to subtract those two, you'll get negative 0.011 Weber. And for calculating the induced EMF, the EMF there was saying is minus N change in magnetic flux over time, as with Faraday's law. If you have to state Faraday's law, we're saying the induced EMF is equal to the rate of change in magnetic flux, which is written like that. And then you are able as well to do the substitution of your 150 loops that we had, the change in magnetic flux and the time taken there. And you are able to know that the induced EMF will be 8.25 volts. The last thing on our question, we were asked to calculate the current in the coil, which we are taking the induced EMF, which is our maximum potential energy that is produced, and that is equals to IR. And then we're able to calculate current, which is 8.25 divided by the resistance of 10 ohm, and we're able to get current of 0.825 amperes. All this is what you have done in the previous grade. And we do that in order for you to see that whatever you have been doing last year is important, because it serves as a foundation for you now as you move to grade 12. Now we move to what we are going to deal with now in terms of our grade that we are in now. We're saying we're going to focus on electrical motors and generators. So we're going to deal with those two. They have the same basic components, are the same, and operate on almost the same basic principles. What do we mean by that? We're saying the components for motors and generators, they will have magnets. Remember, a magnet, I've shown you, it has the north pole and the south pole. And we're saying the magnetic field is from north to south. So all the time, magnetic field, you will see when I show you the structures, you will see that the magnetic field will move from north to south. And then we'll have the coil. You don't have to be confused here, because sometimes we'll talk about the coil, sometimes we'll talk about the armature, sometimes we'll talk about the loop, but we're still referring to that which we are using there. So don't be confused by the language that we're utilizing. It can be the coil that we are using, or the armature, or the loop, will be referring to them in that way. The issue of slip and split rings. So you see, those are the three basic components of the motor and generator. Remember, learners, if you are having a slip ring, you will see this is for AC. Whether it's a motor or a generator, when it has slip ring, is AC. You will see slip rings will be having something of that nature. Slip rings, they will be like that. And then when you say split rings, we'll be talking about a ring that has been split. So you just look at a ring that has been split and it has brushes. So you see these structures here, we refer to them as carbon brushes, which are for electrical contact. So you'll be able to see them when I show you the diagrams, but it's important that we have a ring that is split. We call it split ring. The other name that we use for split rings, we refer to it as a commutator. So it's important that you know these components, because they are going to help us as we answer the question. So we're saying for AC, we use the slip rings, which are like that. And then for DC, we use, you can see the D there. There's a D there. It says for DC, you're able to see that it has a D there. You are able to see that that is a split ring. That is for direct current. We can say split ring, or we can refer to it as a commutator. So you can use that name interchangeably as and when you want to refer to it. Now, the principle was saying, when you have a changing magnetic field, current, it will induce electric field, the changing magnetic field. So when the magnetic field change, when we have changing magnetic field, that's when the EMF will be induced. And when the EMF is induced, there will be current. Remember, EMF is electromotive force. It's this force that will make the charges to flow. And when the charges are flowing, we're talking about current. So you're able to know that as we're having here, we'll have magnetic field, which must induce electric field. I've shown you how to change the magnetic field. I said the movement of either the coil or the magnet. So the magnet, the coil can move in and out, can move in or around the magnets. Then we are able to have magnetic field, change in magnetic field. And if we have change in magnetic field, we're going to induce electric current. And we're saying magnetic fields interact with one another. we'll talk to that as well. What are the basic differences between a motor and a generator? The main thing is the energy conversion. Remember I said motors uses electricity, which means a motor converts electrical to mechanical. You can't write like that in your exam. You can't say a motor converts from E to M. You write it in full, from electrical to mechanical. And a generator converts from mechanical energy to electrical energy. So the difference there is that. And what are the examples? Electric fan, a fan that you are using there at home, is using electricity from the wall and then is able to convert it to mechanical energy, which you are getting that when it's cold and all that. Now the generator example is a bicycle lamp that we use as well. Is using mechanical energy. As you are riding a bicycle, you are converting that to electrical energy that is powering your lamp in your bicycle. So you are able to see that this is how this works, and it's practical. It's something that we use on our daily basis. So the main difference between electric motor and an electric generator is that a generator uses electricity. A motor uses electricity. You can see that a motor uses electricity, but a generator, like you will do when you have load shedding, a generator will produce electricity. So the difference is that the other one is using, the other one is producing. So you must always remember, is this one we said is mechanical to electrical because it's producing electricity, whereas for a motor we are saying is from electrical to mechanical. So that's the main difference between the two. Given you here the direct current motor and direct current generator. Maybe the first question you're asking yourself is, how do I know that this is a motor, and how will I know that this is a generator? It's a good question. Remember what I said. A motor converts electrical energy to mechanical energy, meaning that we must have a power source. So we're having a power source on a motor. A motor will have a power source. There must be. Sometimes we'll show it as a battery like that. Sometimes we'll just show it as positive and negative. Remember a cell, how we draw it. You are able to see that it's positive and negative. If there is a power source, that must be a motor. And how do I know that this is a generator? There is no power source. There is a voltmeter here that is measuring the potential difference there. Then you are able to know that this one there is output here. There is no input, there is output. Is producing electricity. Hence, this will be generator, this will be motor. A motor has power source. It needs power source. There must be input of power. We're using a cell or a battery. And then, but for a generator, because it's producing electricity, in it, we won't have a power source. We will have output. You can put a light bulb that is using the electricity. I talked about a bicycle lamp as well, that as you are riding a bicycle there, you are having mechanical energy and that is being converted to electrical. Then you see your lamp is lighting. So you're able to know a generator must produce electricity, and that electricity we can be able to utilize it. So you see the difference now between a motor and a generator in terms of how they look. Now, let's look at the components. It's important. I want to emphasize that I've already told you that when you see that circle that is split into two, you know that is a ring. It has been split. We refer to it as a split ring. I said you can call it split ring, or you can say a commutator. So it's fine. You can call it a commutator, or you can call it a split ring. And when you use a split ring, you know it's for direct current. It doesn't matter whether it's a motor or a generator. As long as you see the split ring, you can see here we have one ring that has been split in between there. So you're able to know that this is a DC generator. So you see the difference. The DC part is on the component itself. It tells you that I am a direct current because I have a split ring. I have a split ring, then this must be direct current. How do you know that this is a motor? It has a power. It has a power source. How do you know that this is a generator? It has no power source, but is producing electricity. Hence, we have our voltmeter there. I hope you got that. I've indicated to you as well when we started with our lesson to say the direct current. You will see that our current now is in one direction like that, and that's how we'll draw the graph. It will look like as we've drawn it there. So be able to see direct current. That's what you are expecting. Now, in terms of the armature, I told you about the armature, the coil, the loop and solenoid and all that we will be using there that we are putting between the magnets. I told you about the magnet to say the magnet always magnetic field is from north to south, meaning that magnetic field would always move from north to south like that. But when it comes to the current, it's always, we're using conventional current. Remember, it moves from positive. So our current will move from positive in that direction. That's how our current will be moving. That eye, you can see the current is moving like that. The current is moving like that. Now, what is of importance is that when the coil is in this position, we are saying that there is maximum interaction between the magnetic field and the current. Remember, the current is flowing like that and the magnet is flowing like that. So you know that when it's like that, we'll have maximum interaction. Meaning that if you were to draw the graph of this diagram that we are having there, you will be able to see that, okay, as it rotates like that, we are going to have, when it starts, you look at the position of the armature or the position of the coil to say our coil is on that position where we say is perpendicular to the magnetic flux. So when it's like that, we are saying we have maximum, meaning that our graph, if I was to draw the graph, it will start from maximum there. It will start from maximum, then it goes, then and then go like that. But what matters is that it will starting from maximum because we have a maximum here. So I want you to understand me very well here to say we have maximum interaction between the magnetic field and our current when the coil is in that particular position. But I will further explain that. Don't worry yourself. But you got to understand that where the graph starts is determined by how the coil is positioned between the magnet. Because if you have the coil that is in that direction, then there will be minimum interaction between the magnetic field and the current, and then your graph will start as this one is indicated there. So it's important that you always remember. We said there are three main components of motors and generator. Number one, we said the first component, we have the magnet that brings about, which has the north and the north and the south pole. Number two, we said we have the coil or the armature. We have the coil, and we said we have a split or slip rings that determine whether it's AC or DC. So in this case, we're saying all these are DC because they have the split ring. You can call it a split ring or a commutator. I hope I was able to explain this. And all the time, when you see a diagram like this, you'll be able to say whether it's a DC motor, whether it's a motor or a generator. For motor, I'm concluding by saying a motor will have a power source, but a generator will have an output that is utilizing or producing. It will show that it's producing electricity. I hope you got that, and when we do questions, you'll be able to remember. I want to further explain the induction, how the EMF is induced in a coil when we move the magnet. Remember, for magnetic flux to change, we are saying it's either a magnet will move or the coil will move. Now, if we are to move now our magnet, remember, we're saying if a magnet is moved relative to a coil, an EMF is induced. It means as long as the magnet or the coil, one of them is moving, there will be change in magnetic field. So when there is change in magnetic field or magnetic flux, we'll say that the change in magnetic flux will now ensure that there is EMF is induced. But remember, if you stop both the coil and the magnet, there will be no change in magnetic flux. When there is no change in magnetic flux, there will be no induced EMF or current thereof. If the coil is connected to a closed circuit, there will be current in the circuit. So you can see as we move this magnet inside here, we're moving the south pole. Remember what we said? We said the coil will become the south pole. When the south pole comes, it becomes the south pole so that it can repel it. Then there will be change in magnetic flux as it moves. As it moves away, as it moves out, then this coil will become, when the south is moving away, the coil becomes the north pole so that it can attract it back. So you got to, at all times, remember all that we talked about. And we said when the direction of movement changes, the direction of the induced EMF as well changes. Maybe if I can just go back to that page, just to indicate something, to say always check the current, how the current flow when the movement of the inducing action, which in this case the movement of the magnet is to the right, you can see that the induced current opposes, in accordance to Lenz's law, it opposes, it goes in the other direction. They say when this one is going away, it's going out, the current will go in the other direction, because we'll always ask you as well, where will the current flow to? I hope you got that and you'll be able to understand. Now, I prefer that to explain the issue of the induced current, to say the direction of the induced current is such that the magnetic field it established tend to oppose the course of the induction. What am I saying? I'm saying as the North Pole approaches the coil, you can see the North Pole is approaching the coil. What happens to the coil? The North Pole is induced in the coil. You can see the coil becomes North Pole. When North comes, the coil becomes North to oppose or to repel the approaching magnet. I've emphasized that because that is very much important. And if the North Pole is withdrawn, it's going away, then you know that the top end of the coil becomes the South Pole. When the North Pole, now when you move it out, it becomes the South Pole so that it can attract it, the leaving magnet. So we use the right-hand rule in order to determine the direction of the current of the ring. So we're going to talk as well the issue of the Fleming's right-hand rule. To say the right-hand rule states that the magnetic field lines produced by a straight chain carrying wire will be oriented in the same direction as the curled fingers. So you can see these curled fingers here, they are indicating the direction of the magnetic field. And then we are saying that with the thumb pointing the direction of the current flow. So the current flow, then that's where your thumb is. So you got to be able to remember that. So I wanted to show that for a motor, when we are using an electric motor, we are applying the left-hand rule. When we are using the generator, we are applying the Fleming's right-hand rule. So we have Fleming's right-hand rule and Fleming's left-hand rule that we apply. Now, the issue of magnetic flux is important. Remember, we're saying for current to be induced, there must be change in magnetic flux. Maybe you're asking yourself, what is this magnetic flux that you are referring to? So now we're saying the magnetic flux represents an imaginary fluid that flows in the direction of the magnetic field. Remember what I said? Our magnetic field is flowing from north. So you can see that north is always away towards south, so it always flowing like that. And we're saying the strength of magnetic field depends on the density of the flux lines there. To say where the field is strong, the field flux lines are close together. When you have more lines that are close together, you know that we have a strong magnetic field. And we're able to calculate magnetic flux using the formula magnetic field strength multiplied by the area. This area, we said it must be perpendicular to the flux lines, which is what we have indicated there. So B times A, which is magnetic field strength, times area, we are able to calculate the magnetic flux. I've shown you even how to calculate the change in magnetic flux as well. So this is the information that you have done in the previous grade, in grade 11, but you are using it still here. Faraday's law, this equation, it simply shows us how to state Faraday's law. We are saying that the induced EMF, which is that the induced EMF is directly proportional. So we're saying the induced EMF is directly proportional to the rate of change in magnetic flux. That is Faraday's law. At least you are able to say it, or you can say that the induced EMF is directly proportional to the change in magnetic flux and inversely proportional to the time. Then you are able to get it like that, and the formula for Faraday's law is given like that, where E stands for induced EMF, and then the change in magnetic flux is given by that, and the time taken is given by that, and the number of loops is given by that. You have done this in grade 11. We have done the activity when we started the lesson. I hope you are able to follow. Now, let's compare this motor and generator, because we're talking about two things, a motor and a generator. The only difference is that it's either DC or AC. I've shown you that the direct current, we are saying we have split ring, we have a ring that is split, that will be direct current, whether it's a motor or a generator. And for alternating current, we are saying that we'll have slip rings that I will show you as well. Now, if you compare them, you must be able to first check energy conversion to say, oh, the motor uses electricity, so it's from electrical energy to mechanical energy, while the generator is from mechanical energy to electrical energy because it's producing generator electricity. Now, we are saying we have the split rings there for reversed current and split rings there for your DC output. Remember, this one it has output and this one it has input. But now the AC supplies replaces commutator and the slip rings here. So you know that slip rings, when you talk about AC or alternating current, we are referring to the slip rings. And then we are saying now it is the force that brings about the rotation. So we're saying when you have current in magnetic field, you're going to have a force. Is that force that we refer to as a torque that is going to make the coil to rotate. How do we increase the strength of this force? We can use stronger magnets. Stronger magnets doesn't mean bigger magnet. No, it's the strength in the magnet. So I want you to understand it like that. Don't say bigger magnet. It's stronger magnets. It's more turns in the coil. Is stronger current through the coil. So you can increase the current, you can increase the turns of the coil, or you can use stronger magnets. But if you want to increase the induced EMF or induced current, what will you do? You will use stronger magnets, you'll have more turns in the coil, you'll have faster rotation of armature. We talked about this when we started with our multiple choice questions. Don't forget that is how we increase the strength of our current, or you increase the induced EMF. We'll use stronger magnets, we'll have more turns of the coil, we'll have faster rotation, or we'll increase the speed of rotation of the coil. Please always remember that, and it will be able to help you as you prepare for your exams. We'll be doing questions as I'm now wrapping up the theory part of things, so that now you can do questions, typical exam questions. Now we're saying two things are important to note here. When we are generating electricity, we are saying there must be change in magnetic flux. That's the first thing that we said. We said there must be change in magnetic flux to the coil for current to be induced. So if you want to induce electricity or EMF, you must change in flux or magnetic flux. Number two, for maximum EMF is induced when the area of the coil is perpendicular to the flux lines. I've shown you that when is in the diagram where it was placed, and then I said there is maximum interaction between the coil and the magnetic field. So we are saying when the area of the coil is perpendicular to the flux lines, then we'll have maximum EMF. I've shown you even how it will affect the graph as well. As we do questions, you will see we'll be asking you how to draw those graphs. That brings to a different wording of the electromagnetic induction. So this electromagnetic induction, when we started, I told you that this is the principle that the generators use. They use a principle called electromagnetic induction, where electricity generating by changing magnetic field acting on a conductor. So we are having the magnetic field that is acting on the conductor, and that changing magnetic field induces current. I've shown you when the magnet, when the south pole or the north pole is approaching the coil, and then I said the coil will become north pole so that it can repel. When it goes away, when the south pole goes away, it becomes north so that it can approach. I was able to explain that to you, and I'm thinking that is what brings about what we call change in magnetic flux. Is the movement of the coil or the magnet relative to one another. So I hope you got that. And then this, when the movement of the magnet is continued, the current is continuously induced. So the main thing here, I'm emphasizing that it is the movement of the magnet, or we can move the coil between the magnets. So in other questions, you'll find that we're having magnets, and then we are moving the coil between the magnets. Then we have induced current as well. So you got to know those scenarios. But one between the magnet and the coil must do the movement. There must be movement. That continuous movement is the one that will ensure that there is continuous induction of current or EMF. The induced current, we say, is alternating current. When do we say it's alternating current? We're saying the movement of the electric charge periodically reverses direction. I've shown you with a graph that for our alternating current is moving like that in terms of the graph. The direct current, the flow of electric charge is only in one direction, and then you are expecting to see the graph just one complete circle like that. So it's very much important to have that in mind. When you see a graph, you're able to see that this is for alternating current or this is for direct current. Now, this alternating current we are saying is only induced while the magnetic field moves relative to the solenoid. You see, we always changing the language, so it's important that you get used to the language that we use for electrodynamics. Remember, every topic has its own language. So since I started, I've been referring to the armature, I've been referring to the coil, I've been referring to the loop, I've been referring to the solenoid. So you see, we're talking about that conductor that is between the magnets to say if you have that, when there's a change in magnetic field flux with the solenoid, when there is that, current will be induced. So we're still emphasizing that induction of current is due to the change in magnetic flux. I think throughout the lesson, that is the language we're using, because when you start answering questions, you must have that in your mind to say, and now we're saying its direction keeps changing, hence it is called alternating current. So our current is not in one direction. I've shown you as well to say if the inducing action was moving to the right, the current was moving on the other side. So you're able to see that this current is always alternating between positive and negative. Then you are able to see that. And then we're saying, how do we increase? I've said this before, but we are emphasizing it as well to say the strength of the induced current, it can be increased. How do we increase the strength of the induced current? Number one, we're saying you will increase the speed of movement of the magnets. You will use stronger magnets. You will increase the number of turns in the coil, which are the three that we talked about. So always remember that if you want to increase the strength of the induced current, sometimes we'll talk to induced current, sometimes we'll talk to induced EMF. Remember, for current to flow, it is the EMF that is making the current to flow. So hence we're using induced EMF, induced current. Don't have a problem with that. And we're saying the main advantage, why do we use, more especially in South Africa, why do we use AC current? Why do you use alternating current? Why do you use alternating current? We use it is that the voltage can be changed. So we're saying this one, when you use alternating current, you're able to change the voltage. So it means we can be able to step up and step down. Remember, at home we're using we're using lesser voltage, around 240 volts. So imagine if now we have to just bring only 240 throughout, so we won't be able to transport much current using the 240 volts. Hence we're saying we must be able to change it up and down so that we don't bring too much to your home, but for the sake of moving the current, we're able to move much current, but when it goes to your home, we're able to step it down so that we use lower current there. So I say because of this property, the current induced by the power stations is alternating current. So you must know that at the power stations there, we are having alternating current. At your wall there, you are having alternating current because we are able to change its voltage. Then it becomes easy for it to be transported to yourselves. Now, I've been talking. Now it's important that we are going to focus on activities. Let's look at the first activity there. We're having explain what happens when the magnet is pushed into the coil in terms of. So it's important you got to see that we are bringing in a magnet, and what part of the magnet is coming in? It is the North Pole. So you got to understand that, okay, when we move this magnet into our coil, what is going to happen is that the coil now will become a North Pole so as to repel the magnet. Then we are going to have that change in magnetic flux, magnetic field. So that's what is going to happen to say, okay, the magnetic field is going to change obviously when we move, because we said the movement of the coil inside and of the magnet in and out of the coil will have change in magnetic flux. And then we are saying that the magnetic field will change as we move the magnet inside. But for 1.2, how will the coil respond? We are saying now the coil will respond by becoming the north pole so that it can repel the magnet that is coming in. You are able to see that. Now, what will happen to the current? Very much important. So we are saying because there is change in magnetic flux, then current would be induced. But remember, for current to be induced, we got to have a closed circuit like that to say if we have a closed circuit, current will be induced. And we said, remember we said the direction of the current is very much important to say how will that current be able to move in this case, because we said it's opposing that inducing action. And then the direction, which is the last question there. So you are able now to respond to all that question to say as you move the magnet inside the coil, the magnetic flux will change. There will be change in magnetic flux. Now, number 1.2, the coil now, because the north pole was approaching, the coil will become a north pole on the left-hand side to oppose the incoming north pole. So when the north pole approaches, the coil becomes north pole so that it can repel it or oppose it. Now, what is the current? We're saying a current is induced when the coil is connected in a closed circuit. We're going to have induced current now in that particular coil. And the direction of the coil can be determined using the Fleming's right-hand rule. So you're able as well to answer all those questions. Now, let's look at the second activity. It's saying, is the inducing of current by a changing magnetic field? So when you change magnetic field, is that the principle of electric motors or electric generators? So you got to know. If we are inducing current, it means we are inducing EMF, which means we are producing electricity. So we produce using a generator. So this question is all about that, to say what are the energy changes here, because you see that for a generator, for a motor, you are saying no, we move here from electrical energy to mechanical energy. But for a generator, we move from mechanical energy to electrical energy, and we're inducing current when we produce electricity. So hence, this is the question here is that this will be electric generator because it induces current. And they're saying explain. Then you explain in terms of energy conversion to say our generator will convert mechanical energy to electrical energy. I hope that helps you. And then what are the two conditions for inducing of a current? How do you induce a current? Remember, the main thing that we emphasize, we said there must be change in magnetic flux. There must be that change in magnetic flux. Change in magnetic flux is the one that will induce current. We talked about that. There must be change in magnetic flux, and the EMF will be induced. And then when we have that closed system, a closed circuit of ours, current will have current that is flowing. And then look at that question 2.3, which is the question that we've always been talking about since we started with this lesson, to say name 3 ways in which the induced EMF or current in a closed circuit can be increased. So it's very much important to understand that this induced, remember we talked about using stronger magnets, increasing the number of rotation on the coil, increasing the speed of rotation. So all those will be the factors that affect, or the factors that can increase the induced EMF or induced current. So you got to remember all of them to say, for the first question, we said is electric generator. Why? Because it transforms mechanical energy into electrical energy or current is induced. So you were able to answer that. But we said for us to have induced current, the first thing that we must have, there must be a change. There must be change in magnetic flux and to the coil, and this must be connected to the closed circuit so that the current can flow. And then for what can we do to increase induced EMF? Because this question is all about that to say to increase induced EMF or to increase induced current, what must be done? We're saying we increase the speed of the movement of the magnet. We can use the stronger magnet. We can increase the number of turns in the coil. So let's at all times remember those three factors that we can be able to use to change that. Now let's look as well on these questions which are our multiple choice questions. Look at 3.1 there. Which of the following statements describes an alternating current? You see questions where you are given different options. You must go through them and check them so that you are able to get the correct ones, and then you eliminate the ones that are obviously wrong, and then you are able to go and choose. So don't be in a hurry to choose the answer. First, understand Roman figure 1 up to Roman figure 4. Let's look. It says it is produced by a battery. Which one is produced by a battery? Alternating current. Can a battery produce alternating current? You are asking yourself. Remember, we said a cell, a battery, those are DC power source. They are direct current. So that those will be direct current. That makes Roman figure 1 to be out. A battery is producing direct current. So you know that A cannot be the answer. So this one is out because it has Roman figure 1. Now let's go. It says electrons change direction continuously, alternating. Current is the electrons that are flowing, and we're saying these electrons, they change direction continuously. Oh yes, they change direction, alternating. Look at the graph. We said the graph of alternating current is like that. They are alternating, the electrons are alternating, they're changing the direction at all the times. So we're able to see Roman figure 2 is correct. Now, what else goes with Roman figure 2? This one, we're saying it can be produced by a power plant. Yes, our power plant, I've explained the importance of AC, that we can be able to step it up and step it down. And we're able to have the right amount of energy that we need in our respective homes. So it's important that Roman figure 3 will be correct. Electrons move in the same direction. That will be direct current. So Roman figure 4 is the direct current. So Roman figure 1 and Roman figure 4, they are out because they explain direct current. But now it becomes straightforward that our right answer is number B, because Roman figure 2 and Roman figure 3. But remember, we're using this multiple choice to teach ourselves so that we always understand that the electrons, how the electrons flow when we're having alternating current. We're saying they continuously change direction and they can be produced by a power plant. So we know that this is number B. You got your 2 marks there. Now we move, without wasting time, we move to 3.2. 3.2 is saying in a coal-fired power plant. So we're having a coal-fired power plant. Steam is used to turn the turbine's blades. The type of energy conversion which applies here is, the first thing you ask yourself, in the power plant, do we produce direct current or alternating current? You will remember we said direct current is from the power source, the batteries, the cells, and all that. So you will know that for the power plant, as we said in the previous question, we're able to say the power plant, they are able to, those are generators, they generate energy. So a generator, it moves from mechanical energy to electrical energy. So this question was more about definition of what a generator is. To say a generator will convert mechanical energy to electrical energy. So I hope you won't forget this which you are doing, and you will be able to enjoy this section and get as many marks as you can. Now we're saying an electric current, 3.3 there. We're saying electric current flows into a page. See there, indicated by X. What is the direction of the magnetic field? What is the direction of the magnetic field? So you will know that the magnetic field will go in the same direction as the clock, and that will be clockwise direction. So it will move in the clockwise direction. And then if we are to move to our next question, we're able to say the answers were B, A, and C. Now we're going to talk to the direct current here. Remember, my bad here to say this is a split ring. Direct current, split ring. Don't forget that. Direct current, split ring. Already when you see direct current, you know it's a ring that has been split. So that must be direct current. So here we're going to try and explain how this direct current functions and how it works. Now you can see now when you look at that diagram, we're saying this is a split ring. We're having a split ring there. Then that makes it a direct current. But we are saying the current in AB turned around, the current did not turn around. So you're able to see that this brush receives the current all the time. So you have, as I indicated, the components of this to say will be having this is a DC generator. You can see we are having the galvanometer there as well, that is showing the induced EMF, induced current. So you're able to see that this is DC. What makes this DC is that we have the split ring. We said we can call it split ring or we can call it commutator. And this split ring is connected to the brushes. You can see we have the brushes that are connected to the split ring. So I hope that helps you to always remember these components. Now you are having now our current here that we are following. Remember, we want to follow this current and be able to see how this current works. So we're saying at 90 degrees, you can see when we say it's perpendicular, it means at 90 degrees, we're having the long sides at right angle to the magnetic field. EMF has maximum value. So it's when our coil is here, is straight like that between the magnet. We're saying there's maximum interaction between the magnetic field and the current that is and the coil that we are having there. As you rotate the current there, when it becomes at 90 degrees, you will have maximum EMF that is produced. It means now, if I was to say to you, draw a graph, your graph will start from maximum, because when your coil is there, the maximum value, then you start from. So you can't start your graph at 0 there. For your direct current there, your graph can't start at 0, because if it's at 90 degrees, it is like that, then it's perpendicular, then the graph must start from maximum. So when you draw a graph, it will start from there, and then it's able to go like that, until you have a complete cycle. So it's important to know that when it's at that position, we are saying that we have maximum interaction. The long sides are at right angles to the magnetic field. Then we'll have EMF value, which is maximum. But remember, you are having your coil that is in this kind of position. But as now it starts to move, then the EMF, it was maximum when you have the magnets, the north pole this side, the south pole this side. But immediately now when it starts to rotate, the EMF is no longer maximum. It starts to decrease. Hence your graph will start from maximum here, but it starts to decrease, and then until it becomes there in that position, then we say now it's horizontal. We say now the EMF is 0. There is no interaction between the magnetic field and the size of your coil. So we are saying that now at that angle now, we will now be talking about minimum or EMF of 0. You will see as we move the statement here. It says as the rotation proceeds because we said when the coil was like that, it was maximum. We have maximum EMF, and our graph is there. But immediately when it starts to rotate, the EMF starts to decrease until it comes at that position where we are saying at 0 degrees there, the long sides are moving parallel to the direction of the magnetic field. And when that happens, we'll have no induced EMF. So to show it nicely on a graph, you will see that this is the graph that we are using to explain that. So you can see that for this motion that I'm talking about here, is starting from the 0 position. So 0 position is this position of the coil. When our coil is like that, is our 0 position, then there will be 0 induced EMF. But as the coil now continue to rotate, when it moves like this, you can see that the EMF starts to increase until it becomes horizontal like that. When it's horizontal like that, you know that we'll have maximum EMF. So you can see here it was like that, it was 0. It started to rotate. When it becomes perpendicular like that, we say now we have maximum. So maximum is when our coil is like that between the magnets. When the coil is in this position, we're going to have maximum. But when it starts to rotate again, you see now it's moving away from that position of perpendicular. It's now starting to move. Then it starts to decrease. Then it becomes like vertical like that again. Then we know that when it's like that, again, we're going to have induced EMF of 0. So when it's 0, you must know that it's in this direction. But when it's in that direction, you know 100% that we are having maximum interaction, we're having maximum induced EMF. And if we have a closed system, we are saying that induced EMF, we're going to have induced current that is flowing in the coil. So you're able to see our graph and see the position of the coil to say as it's like in that position, we're going to have 0. As it starts to move, the EMF starts to increase. As it becomes back to that position that is perpendicular to the magnetic flux, we're saying that that is maximum that we're having. It starts to decrease again. Then after decreasing, it becomes like that. So you can see, but why is the graph always in one direction? Because we are referring here to direct current. If it was alternating, we're going to talk about another type of graph. So you're able to see that graph and draw, and that is one complete cycle. Remember, a cycle is 360 degrees. So it moved from 0, 90, 180, 270, and 360. And you can see that at 0, at 180, at 360, we are decreased, we're having 0, no induced EMF. But immediately at 90 and 270, we're having our maximum in terms of how that graph was drawn. So I'm hoping that you will understand this type of graphs, and as and when you get it, you will be able to do it. I've repeated this question many times to say how do we increase the strength of the induced current. We said the speed of the movement of magnets must increase. We must use a stronger magnet. We must increase the number of turns in the coil. We must increase the number of turns in the coil. I hope you have that and it will help you as we move now. I'm going to give you this activity just for I won't give you much time. I'll just give you 3 minutes for you to look at the activity and try to answer those questions. Only 3 minutes. Our 3 minutes starts now, and then in 3 minutes time, I'm coming back. We are doing the solution. Just answer those questions and see whether you have understood what we have done so far. Thank you. See you after the break. Welcome back. Hoping that you have done the questions and you have understood them and you are enjoying the section as well. So the first question was, we have a simplified sketch of a generator. So we are told that it's a generator already. Even if we're not told, how will you know that this is a generator? You would look at it and say we're having that galvanometer there, so you know that we're going to be able to look at our induced EMF and induced current there. So you know that, okay, now this must be a generator because there is output, there is no input. We don't have a DC source that we're using, power source that we're using there. Then you know that is a generator. Now, what type of a generator is this? Remember, we said there are two types of generators. We said we have DC generator and AC generator. How do you know that is a DC? We said a direct current, you will see it by having a split ring. It's a ring that has a split, has been split between it. You can see we're having a split ring because I said to you, whenever slip rings for AC, they will be like that. So you're able to see that this one is not AC, must be like this, DC must be like that. So you know that this is a direct current generator. The type is a direct current generator. Explain your answer. Why are you saying this is a direct current generator? You are saying it's a direct current because it has split ring. Remember, we said you can refer to it as split ring or you can refer to it as a commutator. So you'll say we have a commutator or split ring. So you're able to answer to that question. Hence, you are saying it's a direct current. Now, give another weight. Oh, it's like now so we said this is a DC because there's a split ring, and then let's say give another weight for split rings used in a generator, and then this will be another weight for split rings. I already told you that this is a commutator. Show the value of the EMF on the graph that correspond with the position of the armature. Remember I said when the armature or the coil is in this position, we are saying we have maximum EMF. So all the time, you know, I've shown you even on the graph, we have maximum and it's DC. Hence, you're going to say this is a direct current type of a graph, but it's starting from maximum. So maximum there, your graph will start from there and it moves like that until you have a complete circle like that. So you know that that is your maximum that we wanted to see to show that this is a direct current, but it's starting now with maximum because the coil is perpendicular to the magnetic field. The coil is perpendicular to the magnetic field. When it's like this, we have maximum EMF. Remember, I said as it starts to rotate, now the EMF starts to decrease as indicated in the graph until it becomes 0, and it starts to increase again until when again it's in that position of 90 degrees or of being perpendicular to the to the magnetic field. We said that that will be maximum. So when it's maximum, it's always when it's like that, then it decreases. Then when it's like that, you know that we are talking about now minimum. That is what we are having. So your graph must start there. So it's important for you to understand the meaning of how the graph starts. If it's starting from 0, you will know that your coil or your armature was in that position. But if it's in this position, your graph will start from maximum. So I hope you got that and you are able to understand and interpret that graph. I hope you did the question and you're able to get all your marks there. What type of energy conversion takes place in a generator? So we're saying in a generator, we convert from mechanical energy, you write in full, to electrical energy. So you're able to answer that question to say, as long as you are referring to the generator, it will be mechanical energy converted to electrical energy. What is the essential difference in the design between a DC and AC generator? You will know that for DC, we said it has split ring, which is a ring that has been split like that. We said it has brushes, carbon brushes for electrical contact. And then for AC, it has slip rings, which in this case we said that is how your slip rings would look like. So please don't forget all of them. They are carbon brushes for electrical contact with the coil. So you're able to see that, okay, we have the brushes for electrical contact there. And then this for DC, we're saying split ring. You can even call it commutator. So you can call it split ring or commutator for DC generator, and you can use slip rings for AC generator. So it's important that you always understand the main difference between these components and how they function. Then you will start to enjoy the topic itself. Now, let's go to your at least more questions that now involves the calculation, that now involves the graphs, and then we see whether you're able to get it. Now, you can see we always start with your lower order questions, like this question that we're starting with here is saying a simplified diagram of an electrical machine is shown below. So you see your machine. Now you're just laughing alone. You are able to check even before you answer the questions. You are able to see that this machine have a power source, which is your cell there. Then you are able to see that as long as you have a power source, this must be a motor. What makes it a motor is that we have a power source. And then we are saying now we have our coil there. And remember, our current always flows from positive to negative. So you know that current will be moving in that direction. And magnetic field as well is always from north to south. So magnetic field will be moving in that particular direction. So Warren, is this machine a DC motor or a DC generator? So you know they are agreeing that it's a DC, but are they saying is this a motor or a generator? You are able to say this is a motor. What makes it a motor? We have the power source there, the DC power source that we are having. Power source is the one that tells us that we are dealing with direct current. Write down the energy conversion that takes place while this machine is in operation. So you know that a motor always we are taking electrical energy to mechanical energy. So energy is converted from electrical energy to mechanical energy. So you are able to see your energy conversion in terms of that. Write down the name of the component A in the diagram. So it's important that you're able to label them and do it, because these first simple questions that we always ask, you're able to respond to them and you build your confidence. Now, A, you can see that's our split ring. It's our split ring. Remember we said you can call it a split ring or you can call it a commutator. So you can say that is split ring and the commutator. So you can see now the importance of us having to spend time knowing these components and what they do, so that we are able now to answer questions and then we're able to do it. In which direction will the coil shown in the diagram above rotate? So now you can see that you had your current that is moving in that direction, then which means you are going to have a force that is going downwards on that right, and then we'll have a force here that is going upward. So you are able now to see that the movement now will be the anti-clockwise rotation of your coil, and then you are able as well to answer to look at the marking guideline to say we said it's a DC motor. Why did we say that? We said it's a DC motor because of the split ring or the commutator, and we said it converts from electrical energy to mechanical energy. Yes, as indicated, we have a split ring, and we said it will now move in the anti-clockwise direction. So that was activity number 5. We move to activity number 6, which says now we're going to include, as well as I indicated, the calculations, so that you can have a feel of how to do calculations to say which one of the following actions will not cause an increase in induced EMF in a coil if the coil is rotated in a uniform magnetic field. So they're saying which one will not, will not. So we want the negative now. Rotating the coil faster will increase induced EMF. You know that. Increasing the strength of the magnetic field will increase the induced EMF. Increasing the number of turns of the coil will, remember those three factors. So have them at all times so that at least when you are asked question. So obviously replacing the coil with a coil of lower resistance is not one of the factors. So you're going to choose number D there. Now, in the simplified AC generator aside, the coil is rotated. If it's rotated clockwise, so the coil is clockwise, rotated in the clockwise direction, like that. And then, in which direction does the induced current flow in the coil? You can choose from X to Y or from Y to X, and on which principle or law is the working of the generator based. So you will remember when we started with the lesson, we indicated as well to say that the generator uses electromagnetic induction. And I'm happy because now on this one, they said it's a generator and it's we're having AC now, because most of our questions that we're doing were DC. So you can see there we have the slip rings, not the split ring this time. These are the slip rings, and then that's what shows that now we're dealing with questions that involve the AC generator. Now we're saying the principle there is electromagnetic induction, and the question 6.4 was saying state the energy conversion that takes place while the generator is in operation. So you know the generator always convert mechanical energy to electrical energy. You can see as we do these questions that we are almost always repeating the same questions, and if you practice as many question papers as possible, you will be able to answer these questions and you will be able to enjoy the section. So now the last question there on calculations, because remember I indicated that we must be able to do calculations as well. Let's look at the first question. The statement says the voltage output for an AC generator is shown below. So it's AC, you see that it's alternating. But now, because we're doing this, you know that our coil is starting now as in that position, in this position. Hence, we have EMF, induced EMF of zero, of voltage there is zero. So meaning that we are starting like that. And we said, remember there, we're going to have our coil in that direction, and then when it's in that direction, we said we're going to have maximum induced EMF, which is 340. So that is our peak, that is our maximum. Then it goes down, then it alternates again, it becomes minus 340 until it becomes zero again. Remember, one cycle we said is 360. Now the questions are as follows. It says write down the maximum peak output voltage of the generator. So the maximum, you must read it from the graph to say what is maximum. This is minimum. Minimum is zero. The highest it goes is 340 here. So that is your maximum peak output voltage of the generator. So you are able to see that our maximum is 340 volts. 340 volts. Now they're saying a stove is connected to a generator above and delivers an average power. So we're given power of 1600 watts. So the question is saying calculate the RMS voltage delivered by the stove. So you got to first have an understanding to say for RMS voltage or RMS potential difference, we are saying this is referred to as VRMS. Now that is what they are referring to say you have to calculate VRMS. And on question 6.2.3 we are saying calculate the resistance of the stove. And if you are to look at the workings of those questions there in your data sheet, you will have seen that we are given Vmax here. Vmax is given on the graph, and when you say calculate VRMS or root mean square value of potential difference, VRMS is equals to Vmax divided by root 2. So you're able to see as I indicated there, then you are able to get your 1 mark for writing the equation. It's very much important that you always first copy the equation, because the question 1 VRMS, you go to the data sheet, you look for the formula for calculation of VRMS, which is that one, and our Vmax, which was our maximum, was 340. So you're able to say 340 divided by root 2 as given there. That's when you'll get your second mark. Then you simply use your calculator. 340 divided by root 2. You are able now to get your VRMS, which is equals to 240,42. So you got your answer. The last question now is saying calculate the resistance of the stove. Still, you go to the data sheet. You know that P average is given. This is our P average that we were given. We were given as well. What else were we given? We were able to get the VRMS as 240. So you go to the data sheet. You look for the equation, that is our power, and our VRMS, which is VRMS squared over R. I think you remember this equation when we were doing power in the electricity section, where you said P equals to V squared over R. So that is the same equation here. The difference, we're using the VRMS there. You copy the formula and then you substitute your 1006, which is your average power. You substitute your VRMS, which is 240,42, and then you cross multiply. Remember, you're having 1006 over 1, then you will have 240 squared divided by 1600, and then if you use your calculator correctly, you are able to get that your resistance is 36,13 ohms. You will have to do more calculations under this topic and be able to gain even much confidence. And I'm hoping that we have started with this section of electrodynamics. You will do a lot of revision and be able to see the difference between your alternating and your direct current. You'll be able to look at the definitions that we talked to, the definition of what is a motor, what is a generator, what is a root mean square potential difference, what is a root mean square current. Those definitions are important. Know how to define RMS voltage or RMS potential difference, RMS current. You must know all those definitions and be able to know all these calculations. And with all that, I'm telling you that you'll be even much confident. And as I usually will always want to say at the end of our lesson, to say anyone who has never made a mistake has never tried anything new. Those are the words from Albert Einstein. I hope they inspire you to practice even much more and be able to learn and know much in terms of these topics that we are doing. This term, we're talking about the electron, and you can collect as many marks as possible from the sections of this term. So I wish you all the best as you practice throughout the weekend these topics and be able to do as many question papers as you can till we meet again. I would like to say see you next time. Goodbye.